Hello, everyone. Now let's practice on multilinear regression using Bayesian approach. We need to estimate beta 0, beta 1, beta 2 up to beta p in general and see which one is significant, which one is not significant, which one has some impact on the response, which one doesn't have impact on the response. So let's practice on the house price data. So run the library, read Excel, and then upload the data, the house price, and then let's look at the data set. Let's look at the first 6 observations. We have taxes as explanatory variable, bedrooms, bases, the price as the response variable, size explanatory variable, lot explanatory variable. So we have 5 explanatory variables and 1 response variable. And let's define those guys. Let's have the same names, like taxes is the taxes, bedrooms is the bedrooms in data set, bases, size, lot. And let me change the price to be smaller values because these values are big. So I would like to have these values by thousands. So I divide by thousands, but you can keep it. It's up to you. And then let's look at the scatter plots, because one of the assumptions for the relationship between the x's and y is linearity. So the relationship should be linear. Otherwise, you should work with the non-linear relationship or the non-linear regression model. So when you look at the price, the relationship with the size is linear, with the lot is linear, with the bases is linear, but is weak. Price with bases is linear, but is very weak. Price with taxes looks like significant, looks like it's very clear is linear. So I do not see any one of the relationship is nonlinear between the explanatory variables and the response. So now I can fit the model. Let's fit the model using the Bayesian approach. So let's run the library RJAX. And I need to know how many values I have or how many houses I have. I will define the number of houses as M. And then we will define the model. As we have done before, let's look at the definition of the model or the definition of the data distribution and the prior distribution. For I equal 1 up to N, I define the data distribution and the RJAX will use it to get the likelihood. So each observation follows normal distribution with some mean and tau square, which is 1 divided by sigma square. Mu I is beta 1, in our lecture note is beta 0 plus beta 1, x1 plus beta 2, x2, and so on. But in this case, I call them beta 1, beta 2, beta 3, beta 4. So beta 1, which is the intercept, why you call them beta 1, beta 2, beta 3? Because when I define the priors, I would like to use only one loop to define all the priors. So mu I equal beta 1, which is the intercept, plus beta 2 times taxes, beta 3 times the bedrooms, beta 4 times the bases, beta 5 times size, last one, beta 6 times lot. So I have 6 coefficient parameters. And the tau square has some prior distribution, but let me go over the prior distribution for the coefficient parameters. For j equal 1 up to n, I define normal distribution for each beta distribution with mean 0 because I don't know it is negative or positive. And with precision very small, which is 1 divided by 10,000. Why 10,000? Because I defined sigma square as 100 square. Very big value for variability. It means very big uncertainty. It means very small precision. And for the taus, I defined gamma distribution because sigma square follows inverse gamma. So 1 divided by sigma square follows gamma distribution with alpha 0.01, beta 0.01. And sigma square, the one I'm interested in, is 1 divided by tau square. This is the definition of the model. And then I will compile and then update and then get the random sample from each posterior distribution. So let's run this one. And then I will compile the model. And I use number of changes 3, and the data price equal price, n equal n, size equal size, and so on. And I see if there is any error on. There is no error because it said the initializing model is fine and there is no error. So now I will draw samples by updating the model I compiled, and I will ignore the first 12,000 observations in the trace plot. Maybe the convergence happen at 12,000. If it happens after 12,000, I will come back and change these values. So let's update. And then what about the random sample? I would like to select a random sample of 30,000 after these 12,000, after I ignore the first 12,000. And I would like to save the random sample from the posterior distribution of all the beta parameters and sigma square. So I gave the variable names beta in general, so he will understand that beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, and sigma square. So let's generate a random sample from each posterior distribution of each parameter. And then let's summarize the posterior the generated random sample from the posterior distribution. And look at the mean, standard deviation, 95 credible set, and so on. So from this one, I can see if convergence happened, because I would like to check the convergence first. So this is the mean of beta 0, which is beta 1 in our model, beta 1, beta 2, beta 3, beta 4, beta 5. I changed them to be 1 to 6 to be simple and defining the posterior distribution. Beta 0 is 6, beta 1 is 0.02, beta 3 is negative 6.3, and so on. But I don't know those guys are significant or not. So you should look at the 95% credible set. This is the lower limit, and this is the upper limit of the 95% credible set. When I look at beta 0, the constant, which is beta 1 in this case, the lower limit is negative, upper limit is positive. It means beta 0 is not significant. I shouldn't include the intercept in our model. What about beta 1? This is the effect of the first explanatory variable, which is taxes. The lower limit is positive, upper limit is positive. This one is significant. Beta 3, which is beta 2 in our lecture note, beta 2 as bed for bedrooms. This one, the lower limit is negative, upper limit is positive. It means bedrooms has no impact on the response variable price. When you look at this beta for the bases, lower limit is negative, upper limit is positive. This one doesn't have impact on the response. This one is positive, this one is positive. It means the size has some impact on the response. I should keep it in our model. And the last one, lot, lower limit is positive, upper limit is positive. This one has some impact. So I should rerun the analysis again and remove the bedrooms and the bases from our equation. But keep in your mind, it is very important to see the convergence happen or not, because maybe I used some data and the convergence didn't happen. So I need to look at the convergence happen or not. So the first step, you need to look at the posterior samples or the trace plot. So let's look at the trace plot. Oh, beta 1, which is beta 0, is fine. The other second one is fine. Third one is fine. Mix it very well, and then very good. Mix it very well. Mix it very well. Mix it very well. Mix it very well. After removing the first 12,000. So based on the trace plot, looks like convergence happened after the 12,000. So let's look at the. So it looks like it's fine. But sometimes I would like to know what is the effective sample size. Because I selected a very big sample, like 30,000 for each chain. So the total number of generated samples is very big. It's 30 times 3, 30,000 times 3. But what about the effective sample size? This one take into account the autocorrelation. Oh, the beta one is only 1,140, although the sample generated is very, very big. And beta 1, which is beta 0, beta 2, which is beta 1, looks like this one is the biggest one, 39,000, because there is no much autocorrelation in the generated samples for sigma squared. But there is some correlation for the other guys. So in this case, I should increase the 30,000 to be something like 60,000. So I will increase the effective sample size. So it will give me more accurate estimation for the coefficient parameters. So you need to rerun again and increase this number. So, but based on the trace plus is fine, I know it's fine, but there is some correlation in the data. How do I know there are some correlation? You can look at the autocorrelation plots. Oh, and also you should look at the Gelman-Ropin diagnose, because this one is very important also to make sure I know from the trace plot looks fine, but let's look at something more formal, like the Gelman-Ropin measure. So let's look at those guys and see the convergence happen after 12,000 or not. So looks like it happens, but let me make this one bigger. After 12,000, looks like it was big a little bit. Oh, this one is something like 13,000 or 12,000. I don't know exactly, but you can increase the 12,000 to be 14,000 or something. This one is fine after 14,000 or 12,000. This one is also fine. This one is fine. Actually, this 1.6, 1.2 is fine. 1.1 is fine. After 13 or 12 is fine. 13 or 12 is fine. And for sigma is actually it looks like wiggly, but actually this one is convergence happen, because see it's very close to 1. Even this one is very close to 1, very close to 1. So looks like convergence happen for sigma squared. And I can increase the Bernstein iterations, or the part I ignore, from 12,000 to be 13,000 or something. But looks in general is fine so far. But I know there are some correlation among the or autocorrelation for the generated samples. So let's look at the autocorrelation. See, there are some autocorrelation, because this one is not close to 0. This one for beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, which is beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. This one for the explanatory variables, and this one for the intercept. And those guys for the first chain, and this one sigma square, looks like after the first leg is almost 0, which is there is no autocorrelation almost in this generated sample. And beta 1, beta 2 again for the second chain. You can look at those guys, the second chain, and you can look at also the autocorrelation for the third chain, and so on. So there are some autocorrelation. So this is why the effective sample size is not that much big for the parameters, for the coefficient parameters, but for sigma square is fine. So you can increase this one to 12,000 and increase this one to something like 50 or 60,000. You will get a higher effective sample size. So, and also you need to, after you do this one, you look again at, you can look again at these guys, these 95% credible set, and remove the ones is not significant and keep the one is significant, and rerun the analysis again, because you need to have an equation or estimated equation, regression equation, that has all the significant explanatory variables. You don't need to have any insignificant explanatory variables in the regression equations that you are going to use to predict the price house at some explanatory variables values. If you have any question, guys, please let me know. Thank you so much, and see you in a next video. Thank you.